Hello again. We are going to talk about what's in section 3.3, and it has to do with the relationship between the first derivative, the second derivative, and the function graphically. So we're going to look graphically at these three things. You already know that the first derivative is a velocity. You know that the second derivative measures acceleration. What we're going to look at now is specifically what the first and second derivatives mean for the graph of a function and even the graph of the first derivative. Okay, so let's start with just a function, a simple function. This is f, and we're going to look at what the first derivative is. So you already know that here the tangent lines to this function are positively sloped. So the first derivative is positive over here. Over here, all the tangent lines would be negatively sloped. So here, the derivative is negative. Here again, the tangent lines are positively sloped, so the derivative would be positive. So we also know that here we know that we have the derivative is 0 here because we have a horizontal tangent. The derivative is 0 here because we have a horizontal tangent. So notice we go from a positive derivative to 0 to a negative derivative where there's a local maximum. We go from negative, the derivative is negative, to 0 to positive when we have a local minimum. So this describes the important features, the important relationship between the derivative and its function. That where the function is increasing, derivative is positive. Where the function is decreasing, the derivative is negative. And where the function hits a local min or local max, the derivative is 0. Okay, let's look at the relationship between the second derivative and the function. So now we're going to look at the second derivative. Okay. Now, what you need to know is we can call a graph over an interval, a function over an interval, concave up or concave down. What does that mean? Concave up means the graph is holding water. That it's curved so that it could be holding water. When it's concave down, that means it's curved so that it looks like it's spilling water. Technically, the way concave up is defined is that if you draw any secant line, any line between 2 points in the same region, if the function's concave up, the function lives below that secant line. If it's concave down, then it lives above the secant line. So here it lives below the secant line, it's holding water. Here it lives above the secant line, it's spilling water. So when a function is concave up, the second derivative is positive. When a function is concave down, the second derivative is negative. Let's talk about why that is. So, just based on these definitions, it looks like in here it looks like the function's concave down. So the second derivative would be negative. Here, somewhere in here, it changes to concave up. So here the second derivative's positive, here the second derivative's negative. Where it changes from negative to positive or positive to negative is called an inflection point. So where it changes concavity is an inflection point. Now let's talk about why the second derivative is negative when the graph of the function is concave down like this. Well, the second derivative is the derivative of the derivative, right? So notice what's happening throughout here. We have a sharp tangent line, looks pretty steep. It gets less steep, so it decreases, and then it decreases even more. It's becoming steep, but it's decreasing because it's getting very negative. So all throughout here, where the function's concave down, where the second derivative is negative, the first derivative is decreasing. So just like, remember when we looked at the derivative of this, the derivative of the function is negative where the function is decreasing. Well, where the derivative is decreasing, the second derivative is negative. If you look over this side, you can see that as you go from one side to the other, the derivative's increasing. So notice too that here at this inflection point, what'll happen is, so we're going from concave down to concave up. Inflection point is where the concavity changes. That's going to be where the second derivative is 0. But we're gonna see that sometimes if we have an inflection point, the second derivative is going to be 0 there. If we change from concave down to concave up, or concave up to concave down, the second derivative is 0. But the other way of saying it, we cannot say that if the second derivative is 0 somewhere, then it's an inflection point. We can't say that. We can say that if we have an inflection point, the second derivative is 0. We cannot always say that if the second derivative is 0, we have an inflection point, because it may not be true. For instance, it's a great eraser, isn't it? For instance, if I have the function f of x equals x to the 4th, we take the first derivative, that's 4x cubed. We take the second derivative, that's going to be 12x squared. At every one of these places, the derivative is 0. The derivative is 0. The second derivative is 0. Is it an inflection point? No. It actually turns out to be a minimum. Actually, not a local minimum, even an absolute minimum. A local minimum and an absolute minimum, because that's what f of x equals x to the 4th looks like. So the point is, we can't always say that if the second derivative is 0, we have an inflection point. We can't always say that if the first derivative is 0, we have a local min or max. We can say, however, that if we have a local min or max on the graph, the first derivative is going to be 0. If we have an inflection point on a graph, the second derivative is going to be 0. So let's apply this, what we've just discussed, let's apply this to a graph like that one. Okay. What we're gonna, okay, let's look at it for a minute. And the question would be, where is f prime positive? Where is f prime negative? Where is f double prime positive? Where is f double prime negative? Where is f prime 0? Where is f double prime 0? So we're given the graph. This is f, right? We want to know all these things. Where's the first derivative positive? Where is it negative? Where is the second derivative positive? Where is it negative? Where is the first derivative 0? Where is the second derivative 0? So let's see. Okay, let's first look at the first derivative. Okay, so where the function's decreasing, the first derivative is negative. So it looks like the function's decreasing all through here, up to here, and here. How do we write that? We write that on certain intervals. So we know from 0 to 3, and we write this as open intervals, because that's the standard way your book writes it. And that makes the most sense. We're saying that for any interval in there, for any 2 points in there, the function is decreasing. We leave off the endpoints. One reason is f prime is negative on that interval. Okay, one reason that we keep it open is it may be that at the point where x equals to 3, f prime could be 0, not negative. So we leave them open. So it's decreasing there, but it's also decreasing. Let's say this comes at 6, this comes at 7. It's also decreasing on the interval from 6 to 7. So the first derivative is negative on both of those intervals. The first derivative would be positive where it's increasing. And it looks like it's 3 to 6. Okay. So now let's look at the second. Oh, we should also say f prime is 0 at x equal to 3 and x equal to 6, right? Okay, we know that for sure. Okay, now what about the set? So we've got that. What about the second derivative? Okay, the second derivative, let's see. So the second derivative is positive where the function's concave up. Okay, let's try to see where the function's concave up. So it's got to be, so here it's definitely not concave up. I mean, where it's concave up, sorry. Here it's definitely concave up, right? That looks concave up. There it's kind of, that looks concave down, right? Then somewhere along here it comes back to concave up. But so it looks like maybe there, maybe there, maybe there. Okay. So it looks like here it's concave up, here it's concave up, here it's not concave up, but here it looks to be concave up, approximately in there. Let's say. Let's put that here. Here it's concave down, right? All the rest of it. So it looks like f double prime, the second derivative, is positive on the intervals from 0 to 2, because it looks like it's scooped up from, let's say, 2.5 to 3.5. It's scooped up all through there. Here, it's scooped up, so it's about 4.5 to 5. And that's it. Okay, then the second derivative would be negative here. It looks like it's concave down here. 2 to 2.5. Here. 3.5 to 4.5. And then all through here, right? 5 to 7. Okay. And then we can say, well, the second derivative is 0 at the places where it changes concavity. So f double prime is 0 at x equal to, well, it changes here at 2, right? It changes here at 2.5. It changes here at 3.5. And it changes here at 4.5. And then it changes again at, where is this? 5. Okay. So given a function f, this is all, here's the graph. This is all we can say about it. Where is the first derivative positive or negative corresponds to where the function is increasing or decreasing. Where the derivative is concave up or concave down corresponds to where the second derivative is positive or negative. And where it changes, where it has an inflection point, where it changes from concave up to concave down or concave down to concave up, then the second derivative is 0 there. Where it has a local max or min, the first derivative will be 0 there. So that's everything, everything we can say about the derivative and the second derivative based on a graph of the function. Now I'm going to stop here and I'm going to continue with this topic with an example of what can we say about the function if we're actually given a graph of the derivative, not the function, but the derivative. That's coming next.